All right, the next example we have, example 3, is to design a cylindrical can with a fixed volume of 900 cubic centimeters so that it uses the least amount of metal. So we essentially want to minimize the surface area if we wanted to use the least amount of metal. So what we can do is draw for ourselves a cylinder. There we go. Now the cylinder has a radius, let's say, of r, and it has a height of h. And we know that the volume of the cylinder is 900 cubic centimeters. The volume of a cylinder is essentially take the area of the cross-sectional circle. So pi r squared is the area of each one of these little circles. And then imagine just stretching one of those circles a distance h. So times h, that is the volume of a cylinder. So this right here is our limited quantity. This is our constraint. Now what we need is an expression for the surface area. So when I look at a cylinder, I think about the two circles that are identical, top and bottom. So we'll have two copies of the circular caps. So we have those two areas. Plus we have the area of the sides, like the around the lateral area. Well, what we can do is imagine taking a pair of like scissors and cutting up the edge of the cylinder. And when you cut this and then unroll it, what are you going to get? You're going to get a rectangle where this length is just the height and this distance across the top is the circumference of the circle. So the circumference of a circle is 2 pi r. Right? That's the circumference. So the area of that rectangle is the circumference, 2 pi r, times the height. And as you can see here, this is the thing we want to minimize, but there's two variables, r and h. So what we can do here is take our constraint equation, solve it for one variable, such as, well, we could solve for r or h, but if we solve for r, we'll have to do a square root. And if you have the choice of doing something that involves a square root or doing something else that doesn't involve a square root, it's usually easier to do the thing where you don't have to take a square root. So I will solve this for h and get 900 over pi r squared. Then we can import that information so that we get a function of the radius r. This would be 2 pi r squared plus 2 pi r times the quantity 900 over pi r squared. You would simplify this a little bit to get, let's see here, 1800 over r, because the pi's will cancel, one of the r's will cancel, and the 2 times 900 is 1800. Perfect. So now we want to think about what interval is this on. So you might be thinking, okay, well, what's the smallest that the radius can be? 0. And physically, sure. But here's the thing. Mathematically, look at this function. If we say 0 here, then that means we have to mathematically be able to plug in 0 into the actual function. But because we have an r in the denominator, that means we can plug in values as close to 0 as we want, but not actually 0. So here, this is where we get to see an example of our first non-closed interval. So we can't include 0. So now you think about, well, how big can the radius be? Well, I mean, if the radius is really big, then doesn't that just mean that the cylinder has to be pretty short? Because the cylinder always has to have a fixed volume of 900 cubic centimeters. Think about if you've ever played with Play-Doh, or if you bake with bread at all and you're rolling out like maybe a baguette or something. Or, if you roll it out, you can make it as long and thin as you want to. But the longer you make it, then the thinner or the smaller the radius is. On the other side of things, you can make the radius very, very large, but then the cylinder isn't very long at all. But there's nothing really that says R can't be as big as you like. R could be 1 billion, but then the height is very small. It's just that the radius and the height react to one another in an inversely proportional way. The larger the radius is, in order to maintain a constant volume of 900, the height has to become, what did I say, small radius, very large height then. So, if the radius can be as small as it wants to be, that means it should also be able to be as large as it wants to be. Now, granted, we can't actually get there, so that's why we get an open interval. Okay, so with this, we can go ahead and begin finding critical points. So we have 4 pi r plus, this will be negative 1800 over r squared. If we do see that this derivative does not exist at r equals 0, but 0 isn't in our domain to begin with, so we disregard that. So we're only going to check to see where a prime of r equals 0. This happens when r is equal to the cube root of 450 over pi. So if we set this equal to 0, we'll add this term over to the other side, multiply the r up and over to get an r cubed, and then 1800 divided by 4 is 450. So that's where we get the 450 pi, and because we'll have an r cubed, we cube root it. So there's our lone critical point. So now we want to compare values. So comparing values, we have a of, well, we can't plug in 0, right? We can't plug in infinity. So instead of writing it like this, we're going to do a limit. So we'll do the limit as r goes to 0 from the right of a of r. What does that equal? Well, look up here. As r goes to 0, this term goes to 0. But as r goes to 0 from the right, we're dividing 1800 by a smaller and smaller positive number. So something divided by a really, 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 really small positive number is really, 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 really big and positive. So this is going to go to positive infinity. And if we do the limit as r goes to infinity of a of r, this term now goes to 0, because if we take 1800 and divide it by a really, really large number, as r goes to infinity, this whole fraction goes to 0, but this term goes to infinity. So we again get infinity. So infinite surface area. But then we can take our critical point. There's no domain issues there, so we can just plug in the cube root of 450 over pi. And when we do so, we end up getting 90 times the square root of 60 pi. And clearly, whatever this number is, it's decimal, doesn't matter, it necessarily is less than infinity. So this is the minimum surface area that we're looking for. So that means the cylinder should have a radius of the cube root of 450 over pi and a height of, well, we have to get the height. To get the height, we would take this expression for the radius and just plug it into this equation right here. And if you do that and simplify, that height turns out to be 900 over pi times the cube root of pi squared over 450 squared. And that's the optimization problem.